It's a bimolecular reaction. That means it needs two different components in the reactants, a nucleophile and an electrophile.
Yes. Next point. I agree.
It's second order.
Correct, because it's bimolecular. Agreed.
There's also a leaving group.
Yes. Keep going.
Substitution reaction.
I agree, it's a substitution. Next points, we have like 3 more, 4 more.
There's an inversion of configuration on.
Inversion of configuration, which means you can start with an R, you end up with an S, or S to R. That's key. Why is there inversion?
Because of the back attack from the nucleophile on the electrophile.
Okay, that's correct. And then, in terms of the electrophile, what structure of the electrophile is favored?
The chiral carbon?
No, I mean.
Wait, what do you mean by that?
I'm talking about primary, secondary, tertiary.
Oh.
So methyl halide is preferred over primary, primary preferred over secondary, secondary preferred over tertiary. Okay, why? Because SN2 dislikes sterics. Yeah, so now these last 2 points will be the opposite of SN1. So SN1 will take the reverse of this. So it's going to prefer tertiary over secondary over primary because of stability of the carbocation, which is what you're seeing here. This happens to be a tertiary because the C plus goes to 3 other carbons like 1, 2, 3. So that's a tertiary. It's more stable. Tertiary carbocations are more stable than secondary. Secondary are more stable than primary. So in fact, primary and methyl X do not do SN1. Okay.
So SN1 can happen with a secondary and a tertiary, but it prefers tertiary?
Yes. In fact, with the secondary, we'll work with SN1, SN2, E1, E2. It's right in the middle of the ranking. Okay, so that's why I had to review what we did with SN2, and then I'm gonna say.
I have one more question.
Yes.
With the SN2 reactions, we have that no reaction will form between an sp2 carbon and an sp carbon. Will SN1 reactions happen with those carbons?
No. Remember I said no substitution will take place, meaning no SN1, okay. No SN2. I'm not even going to list them here. They are no-go zone. Good question. So sp2, sp carbons will never work. You have to have sp3, and then out of the sp3, you have to identify them as methyl halide, primary halide, secondary halide, tertiary halide, or tertiary carbon, secondary carbon, primary carbon. So I'm disregarding sp2. sp2 and sp, those guys, don't even consider them. It's no reaction. And in fact, for methyl X, it will never do SN1. Primary will slightly want to do it, but I would also consider it a no reaction for SN1. Just like with SN2, tertiary will say no reaction for SN2. So for SN1, starting from primary going backward, you need to say no reaction. We'll explain why. Alright, so SN1, it's still a substitution. You need a nucleophile, but the nucleophile does not determine the rate. It comes afterwards. Only the electrophile determines the rate. That's why it's unimolecular. One thing determines the rate of reaction. So in this case, the electrophile, we'll call it electrophile. We call it an electrophile, but the term used here is substrate. Why? Because it's the only one in the beginning that plays the role, takes part in the first step of the mechanism. Okay, so right
It's
here.
just
So I said this was a SN2 review. The summary of what we did, I think, the last two classes. We said it's bimolecular, so two things determine the rate: the nucleophile and the archy halide. And then you need a living group. That's what LG means, not the fridge company. You need a living group. And then it's a second order because two things determine the rate. It's a substitution. You get inversion of configuration because of the back attack by nucleophile. And then right here I was trying to say sp2 and sp must not be considered. So the reaction profile with the electrophile is methyl X, X being bromine, iodine, chlorine, any halogen except fluorine. So methyl X will react faster than primary, than secondary, than tertiary because SN2 is hindered by sterics. That's the summary. Have you noted everything down?
yes.
Okay. So now let's proceed. So I was mentioning that for SN1, only one structure determines the rate, which is going to be typically the electrophile, what needs to be attacked by the nucleophile later on in the mechanism. But the key rate determining step, we call it RDS, the rate determining step, is governed by formation of the carbocation. So the living group just randomly falls off. You get the carbocation. So for example, if you have a tert-butyl bromide, the very first step for SN1 is loss of the living group. And that's what we call the rate determining step. If you've not formed the carbocation, the mechanism is not going forward. So only then the nucleophile can come and attack, which means the nucleophile does not affect the rate. Okay, so only the electrophile affects the rate, not the nucleophile, and that's why it's unimolecular. One molecule determines the rate, which happens to be the substrate that makes the carbocation. So that's what's happening here. You lose the living group. In my example, that was Br. You make your carbocation. Notice that the carbocation is sp2 hybridized carbon. Has the sp2 hybridized carbon. You have 3 electron domains, the 3 bonds, 3 single bonds. So it's sp2. So the nucleophile can attack either from the top or the bottom. Remember, sp2 hybridized carbon centers are trigonoplanar, according to test 1. They are trigonoplanar. They are flat. So the nucleophile has 50% chance attacking from the top and from the bottom. And for that reason, you might have a 50-50 mixture of RNS. Whenever you end up with a 50-50 mixture of RNS, that condition is called, those products are called racemic products. It's a racemic mixture, like from the word race. This only happens if your products turn out to be chiral. You have 4 different groups around the carbon center. So it's 50% R, 50% S. It's equal mixture, so it's a racemic mixture. If the product form does not have 4 different groups, you only show one product. When it forms chiral products, then you're going to have equal mixture of R and S, 50% of one, 50% of the other one. That's called racemic mixture. So that's kind of the overview of what we're going to be discussing in detail today. And then we'll say, you remember SN, we forgot to say something here. For SN2, it prefers aprotic solvents. That's another one. It prefers aprotic solvents, of course, and it also prefers strong nucleophiles. For SN1, it's going to work with weak nucleophiles, and it's going to prefer protic solvents. So it's going to be the opposite. So SN1, you'll have weak nucleophiles. Okay? You'll have protic solvent needed. And of course, like I said, the trend will be tertiary is more reactive than secondary. Secondary is more reactive than primary. Primary, of course, we don't even need to rank these guys because primary and methyl X will not do it. And then, of course, it's unimolecular. And then I just said can make racemic mixture. Okay? So you equal mixture of R and S. SN1 can do that. It might give you racemic mixtures. SN2 never gives you racemic mixtures. It's just one product. So keep that in mind. And we're going to be breaking this stuff down, these points down in this chapter. I hope you finish writing so I can continue. All right, so let's look at the next one. So, like I said, the rate of reaction for SN1 is gonna be unimolecular. I mean, the rate of reaction, it only involves the electrophile, so that's why SN1 is unimolecular. Only the electrophile determines the rate. So the question will be, well, don't worry about K. K is found from the lab experimentally. So the question is, what will happen if the electrophile concentration is doubled? The rate is going to double. So if you double the concentration of the electrophile, the rate will double. If the concentration of the nucleophile is doubled, the rate does not change. It would have changed in SN2 because remember in SN2 our rate equation was rate equals to K, concentration of the nucleophile multiplied by the concentration of the electrophile or the substrate. So the nucleophile took part in the rate equation, but here in SN1 the nucleophile is missing in action. So it doesn't matter how much of the nucleophile you add in the reaction, it's not gonna affect the rate. Only the concentration of the electrophile affects the rate. So whether you double the concentration of the nucleophile, you triple it, you quadruple it, you multiply 10 times, no change in how quick the reaction will go, how fast the reaction will go. And therefore, the overall SN1 reaction has to go through a series of steps. So first, the electrophile will make the carbocation intermediate. Okay? Rate determining step. Make the carbocation before the nucleophile comes to attack. That's why SN1 goes through a series of steps. Remember, in SN2, the reaction is concerted. Reaction is concerted. It happens at once. But in SN1, the reaction is not concerted. That's a trivial point, but just know that SN1 goes through multiple steps, at least 2 steps. SN2 goes through 1 step. Okay, so let's look at a reaction. So remember, the key step is formation of a carbocation. I cannot emphasize that enough. So you form the carbocation first. So this bond of the leaving group wants to break. So that's why we have the dash bond, the hatched bond, because this bond wants to break. The chlorine wants to fall off. Once chloride falls off, which is gonna be right here, once it falls off, you make a carbocation. Positively charged species are called cations. This cation is, the plus sign is sitting on a carbon, so it's carbocation. Now, usually, this is what you'll see on the question. You'll have that and H2O and methanol, or let's say generally any other alcohol. So these guys are weak. These are weak nucleophiles. You see, they are neutral. They are not negatively charged. Strong nucleophiles should be negatively charged. That's why I say SN1 works with weak nucleophiles. And of course, this one is tertiary. SN2 has no chance to happen. The backside is hindered. So the very first step is for the Cl to fall off. You're going to end up with a positive charge. And then now your weak nucleophile, e.g. water of any of the alcohols, will either attack from the top face. You see where the nucleophile is coming in after formation of the carbocation. So the nucleophile does not determine the rate. The rate determining step is right here, formation of the carbocation. So now the nucleophile will come up on the second step. Remember we said SN1 goes through a series of reaction steps. So you attack either from the top, or you attack, the nucleophile might decide to attack from the bottom. The reason being, the C plus is sp2 hybridized, which means the molecule around there is trigonal, planar, is flat. So the nucleophile has equal chance of attacking from the top or bottom. So if it attacks from the top, this is what you get as a transition state. I remember telling you not to worry about drawing transition states. Transition state is where a bond wants to form or a bond wants to break. So now attacking from the top, this bond in red is actually this bond that wants to form here. This arrow in red is this bond that wants to form. Now oxygen will technically have 3 bonds around it. The formal charge will be positive character, partially positive because the bond has not fully formed. Once the bond is fully formed, now you have a full positive charge. Okay, you attacked the carbocation using your water, your nucleophile, which could also be any other alcohol, using the oxygen to attack, or even ammonia. Any element with a lone pair will do this attack. So now once you get this structure, we call it an intermediate. It's not a carbocation intermediate, but it's an intermediate. It's not yet. We don't have the product yet. So it's an intermediate step. So next we do what we call proton transfer. So another molecule of water comes to take out the extra hydrogen from this structure here. And then now you get OH, which is neutralized. The oxygen gets neutralized. And then the water that takes the proton makes H3O+, which is called hydronium ion. And of course, once you steal that extra proton by proton transfer with the water, another molecule of water, you're going to end up with an alcohol. So typically, in this equation, where's my pen? Lost my pen. So in this equation, if you do this reaction, you should end up with OH where the Cl was. So definitely, that's a substitution reaction. Why? Because you started with a Cl, go through the whole mechanism, you end up with an OH. So that's why it's called a substitution reaction. And it's SN1 because it's not concerted. Of course, this is tertiary. SN2 fails here. There's another reason why SN2 fails. The solvent, which happens to be the nucleophile, is protic. SN2 fails. So there are 2 reasons why SN2 will fail. You have a tertiary electrophile and you have protic solvent. So SN1 will work, not SN2. Remember, that's the goal of this chapter. We are learning much about SN1, but still going back to compare to SN2. You know, in exam 3, there's usually like 3 or 5 sets of questions which ask you which reaction will happen here. Is it SN1, E1, E2, SN2? Then you have to specify which reaction happens. And to do that, you have to know the conditions that favor which reaction. So right now we are comparing SN1 and SN2. In chapter 9 and 10, we'll talk about E1 and E2. Those ones are easier. Okay. Let me ask a question. How many endothermic steps are happening here? Oh, actually you're shown, so I don't want to ask that question because it's already shown. So from here to here, it's endothermic, because reactants are lower than the product, which happens to be the carbocation intermediate for the first step. And then from the carbocation to the other intermediate is exothermic. This will now be your new reactant, and this will be a new product. So it's exothermic. And then from the product, from this second intermediate to your products, let's say this will now be your new reactant, 2 circles, to give you a new product, 2 circles, is exothermic. Overall, this reaction is exothermic. Now, you definitely see that you're going through multiple steps. In SN2, all we had is one transition state. Why? Because the two molecules reacted at once. That's why SN2 is bimolecular. Okay. In SN1, one molecule first makes the intermediate, and then that intermediate is going to be attacked by the nucleophile, and then proton transfer to give you the product. So there are multiple steps in SN1 before you get to your product, and that's why SN1 might take longer to happen than SN2. Okay. So let's see another example. Can someone tell me what type of electrophile we have there? Is it primary, secondary, tertiary, or methyl halide?
Tertiary.
Thank you. This is tertiary. And because it's tertiary, we don't expect SN2 to happen. Instead, we expect SN1. And again, this is protic. So that's protic. SN2 is going to be disfavored. So the first step is to lose the leaving group. You get your carbocation intermediate. Okay. And now once you have your carbocation intermediate, it can attack from the top face. You notice the mechanism is very similar. Or it can attack from the bottom face. Okay. So if it attacks from the top face, these groups that are on the plane, remember that's sp2 again. You see there's a shaded blue surface. That implies that you have a planar geometry right there. So you equally approach from the top or the bottom. So let's follow the blue attacking from the top. These alkyl groups that are on the plane will be flashed down because you're attacking from the top. So that's why these groups are flashed down, attacking from the top. If you attack from the bottom, these groups will be flashed up. You see, they're flashed up. Pathway B. And now you don't stop there. You have several molecules of this water, the weak nucleophile, I should say. It's a weak nucleophile. It's substitution, so this plays the role of a nucleophile. Okay, so next step is proton transfer. Take out the extra hydrogen, neutralize the oxygen, giving it the 2 electrons. You end up with your tertiary alcohol. This hydronium comes from whenever the water picks up the extra hydrogen. It gives you the hydronium. So same thing here. You get your water picking up the hydrogen. You get your hydronium byproduct. After proton transfer, you get your alcohol. Now, I hope you guys know how to assign stereochemistry, Because we have two approaches, A and B, one product will be R. Obviously, you have to do some rotation. Well, let's see. This one you don't need rotation. Let's see if we can assign priorities. So oxygen will be 1, propyl will be 2, ethyl will be 3, methyl is the smallest group. So you're going 1, 2, 3. And this question was poorly done in the test. I don't know why. Maybe you are scared about the molecules looking big, but it's the same thing. I wonder why you did not do well, most of you. So this is an R. We keep it as an R. The smallest member is at the back. So same thing here is 1, 2, 3. The smallest group is at the back. Okay, so now here we are going 1, 2, 3. That's an S. So because you have 50% chance of approaching from the top, 50% chance approaching from the bottom, that's why you have equal 50-50 mixture of R and S of the alcohol. That mixture is called a racemic mixture, which is part of the summary I gave you on the first board. Do you have a question? Unmute, ask. Looks like my explanation is clear. Someone give me the answer to that question.
The first one?
Okay, let's see. So this is the CH3. I think I agree it's the first one. That's the answer. So you have 3 multiple CH3s. So that happens to be this part on the molecular, condensed molecular formula. This carbon in the middle is this carbon. And obviously you have a bromine, which is this. Notice that the nucleophile, of course it's a weak nucleophile, it's not negatively charged. The nucleophile is not included. This is the correct rate reaction, equation of reaction for SN1. And it's SN1, again, because the substrate or the electrophile is tertiary. SN2 has no chance. The other reason is the main reactant, which happens to be the solvent, is protic. Of course, again, it's a weak nucleophile. SN2 will want strong nucleophiles. This is protic. SN2 will want strong nucleophiles. This is weak nucleophile, so SN2 will not happen. This is protic solvent that's mixed with another solvent which happens to be a protic, but because we need lots of water in this case for this to work, you mostly have the water. So the environment is mostly protic, so SN2 will be disfavored. Anyway, it's substitution because at the end, Br is substituted with or replaced by the OH. So I agree. The correct answer is 1. Only the concentration of the electrophile or the substrate determines the rate. So we are going by that general formula. Okay, I think there's another question. What is the answer to that question? Someone help me out. What are the major substitution products formed in the reaction? This is a
Is the only difference of them their stereochemistry?
Yeah, it's good. There's gonna be a difference in stereochemistry. So what's your suggestion?
My guess is 1 and 4.
1 and 4. Okay, let's see. So first, this is a secondary, so it could go either SN1 or SN2. It's secondary substrate. So we have to look at the arrow and see what's going on. Obviously, this is not negatively charged. It's going to be a weak nucleophile. So remember, whenever we used water, we ended up putting OH, not the whole molecule in the product, right? So we do the same thing here. We are using ethanol, so I'm going to just draw without showing the other hydrogens like that, which means we at least have to lose one hydrogen. Then the rest of the molecule should be put on the structure. That's the shortcut. So for H2O, we lost one hydrogen, we put the OH on the molecule. For alcohols, generally, no, during the mechanism, there's going to be the last step, which is proton transfer. Let me take you back. You see, this step right here is a proton transfer. You lose the hydrogen of the water right there. So which means for the alcohol, you lose that hydrogen at this step, proton transfer. So the shortcut is this OR group will be attached on the molecule. In this case, it's the ETO, or the CH3CH2O. That's the part that's going to be attached to the product. Okay, so that's what we need to put on the product eventually. Okay, so that's why you see all these OCH2, OCH3, because eventually that's what will happen. Are we affecting this part? Nope, that stereocenter is not changed. So based on that, I can quickly nullify 3 and 4. Because in 4, it's showing that this was changed. We did not do any change. We did not attack that carbon. So 1 and 4 is out. So the correct answer is 1 and 2. So the answer is C. The reaction only happens where the Cl fell off. The CH3 stereochemistry is conserved. What is the relationship between these two guys? Are they meso compounds, enantiomers, diastereomers?
Diastereomers?
Correct. And it's because one stereocenter is kept. Obviously, I said with SN1, it's not going to attack the metal stereocarbon, the chiral carbon on the metal. So these guys are diastereomers. It's usually a follow-up question after this. So you have two major products, 1 and 2. And the reason is, once the Cl falls off, you get an sp2 carbocation center, so the ethanol can attack from the top or the bottom. So this here, the ethanol attacked from the bottom, attack the carbocation from the bottom. If you forgot what a carbocation is, it's going to be this structure right here. So the ethanol can attack from the top. That's how you get 2. Or it can attack from the bottom. That's how you get 1 with this bond, which implies away. This one implies towards or on top. Is that clear? You have a question?
I have a question.
Yes, please.
With SN1 reactions, because you're only attacking one chiral carbon center, would it always result in a diastereomer or not? Because one would stay the same and one would change all the time.
So you're asking whether it always attacks one carbon center?
Yes.
It's not always. It depends on whether you have several leaving groups. You know, here we only have one leaving group, the Cl. Sometimes you have 2 Cls.
Okay.
So to answer your question, I'll say the nucleophile will always attack the carbocation center for SN1. And the carbocation center must be formed after the leaving groups leave. So it may attack several centers. Depends on the number of leaving groups.
So if you have more leaving groups, would that add more steps to the reaction, or
yes,
would it just happen?
It goes crazy, but that's not for your survey organic class.
Okay.
So for you guys, I just give you 1 center. Leave that for the crazy ones. That's tough. Whenever you get such a question, that's tough, because you go 1 step forward and ask yourself, which leaving group will leave first before the other one? And that's the technicalities I don't want to bring in this class. All right. So let's move on. So, well, give me the answer to that.
B.
Yes, diastereomers. because again, you're not gonna touch that site. Remember again, assume the OH is gone because it's gonna go by proton transfer in the mechanism, so it's easy to predict here. For now, I would say for now, because after this we're gonna talk about carbocation shifts and migrations, methyl shift, hydrogen shifts. Those has to be considered. Okay, so those are the two products, and these two guys are diastereomers because one center is kept. This chiral center is kept, the other one is switched. If you want, you can assign RNS. You'll see that the methyl chirality will stay, but the ether chirality will change. Okay. All right, so let's see. Good leaving groups are those that form stable ions or molecules after they depart. We already discussed in SN2 how to know whether something is a good leaving group. It's the same factor here. Remember, good leaving groups must form weak bases. Just to give you a review, there's a video we recorded on leaving groups, so refer to that to know how to judge the leaving group propensities. So I'll not reteach that part. So just remember, weak bases are made weak by resonance stabilization. We discussed resonance stabilization. We discussed size. The bigger the size, the better the leaving group. For example, iodide is a better leaving group than F-, because they're on the same column, so we consider size. The other factor is electronegativity that we discussed. So these are the main factors that make leaving groups stable. So you really want something like iodide is big and electronegative. You don't want OH as a leaving group. You don't want, for example, RO- as a leaving group. For example, methoxide, alkoxides. These guys are strong bases. And because they are strong bases, they are poor leaving groups. So that's the summary, but again, we discussed about that before. Okay, some leaving groups are stabilized by resonance. So if you have these guys sitting on a tertiary carbon, for example, when the group falls off, so like, let's say you have, and this is just for your eyes, I won't bring this in your test. This is usually covered in the official organic class. So let's say you have this big structure. Once it falls off, it's going to give you this structure as a conjugate base. You see, it's resonance stabilized. Weak bases make strong acids. The pKa is negative 1.03. The lower the pKa, 1.3. The lower the pKa, the stronger the acid. So just know there is resonance stabilization. Like I mentioned in the previous slide, resonance stabilization makes good leaving groups. That's a key point here. Resonance stabilization helps leaving groups to leave, because after they leave, they will be stabilized by resonance. The electrons are pushed around the structure. Okay, all these guys are resonance stabilized, so they are good leaving groups.
So resonance stabilization makes good leaving groups because instead of the electrons interacting with another molecule, they just jump around their own molecule.
Yeah, exactly. They jump around, they are hidden within the structure of the molecule. You know, a strong base should have electrons available to attack another molecule. But because of resonance, the electrons are hidden within the structure. It's just like you having money in your hands, and then you decide you're going to put it in your pocket. Then that money is not available to be stolen, right? That's the thing here. So instead of exposing the electrons, the molecule decides to hide the electrons within the structure, which makes the molecule a weak base. It does not easily use those electrons. They are hidden within the structure by resonance. So you're right. The resonance helps to keep the electrons away from attacking another molecule, and that makes the molecule not to play the role of a base. Okay, we talked about that. So which of the following compounds will be the most reactive? Order the following compounds from the most reactive to the least reactive. Which is the most reactive?
The first one?
Yes, I'll go with the first one. Again, this is a tertiary carbon. That's tertiary carbon. How do I know? The carbon is bonded to 3 other carbons, so it's tertiary. The carbon in the middle, holding the leaving group, is bonded to 3 other carbons, or there are 3 bonds going outwards to a carbon. This one is tertiary alcohol. Again, you have 3 carbons from what we call the alpha carbon. Actually, that's called the alpha carbon. We talked about it last class. So SN2 will not work, so SN1 will work. So first step of SN1, lose the leaving group. You're gonna get a tertiary carbocation. But the key point to answer this question is the structure of the leaving group. So same thing happens here. Your leaving group will be that. And then here, if OH leaves, it's gonna give you that. Obviously, this is a strong base. Br is farthest to the right of your periodic table. Remember, electronegativity increases across the periodic table. So Br is somewhere right here. It's to the farthest to the right. So it's more electronegative than oxygen. So Br is the best leaving group. It's electronegative and it's big in size. 2 factors favoring Br as a good leaving group. It's stabilized by size and it's stabilized by electronegativity. So Br wins. So the first one will be the most reactive, followed by this one. Both this leaving group and the OH minus have oxygens bearing the negative charge. And because of that, we cannot consider electronegativity. Instead, we consider resonance. The structure here can do resonances. OH minus cannot do resonances. So the second structure will be more reactive than the third structure. And the reason is, again, the stabilization, how stable the leaving group is. You consider resonance, consider electronegativity, consider size. So this is the most reactive because it has the best leaving group. The weakest base, Br minus, is the best leaving group. All right. Next, which of the following alkyl halides will react slowest when reacted with aqueous? Aqueous means you have lots of water. Aqueous solution of acetone. Someone tell me which one will be the most reactive and why. Someone?
4.
Would it be 3 because fluorine is larger or smaller?
No, fluorine is actually the smallest out of the halogens. So you have FCl, Br iodide. Size increases down. So let's see, which of the following will react slowest? So slowest will be 3, because this is the smallest. When this falls off, you get F minus is the smallest. I minus will be the fastest. So the one that will react slowest will be fluorine. fluorine alkyl fluoride. Factor consider is size. F minus smallest, so it's least stabilized. Fastest, biggest iodide, that's the most stable leaving group. So if the question was asking which one will react fastest, answer would be 4. Which one will react slowest? Answer is F. So if you are to rank, you'll say 3 will react slower than 2, 2 will be slower than 1, 1 will be slower than 4. Okay. Do you have a question on that? Okay.
Is the larger halides react faster because their size allows them to like conform their shape more? Is that why?
The iodide will react faster because, okay, you know, it would have conformed. Okay, the thing is with conformation of shape is it's if you're using the I minus to attack a carbon center, but here we are looking at it as a leaving group. So what you want to think about is you have more volume of the negative charge to stay in there, right? So you know negative charges will repel. You don't want them to be very close. So with F, the negative charge volume is very close. So the molecule is so unstable, it wants to dispense some of those negative charges by reacting, by attacking another molecule. But with iodide, because of size, the negative charge are dispersed. We say they are delocalized. The electrons are well delocalized or polarized. Of course, with polarization goes with conformation of shape, like we described last time. All I want you to keep in mind is the volume or space available for the charges to hang around within the anion, the I minus. That's why. Okay, so let's talk about the solvent effects. So the first one, we've talked about the leaving group, how it affects SN1. The second one is solvent. Remember, the bottom line I gave you is SN1 prefers protic solvents. So we are about to explain why do we need protic solvents. Why don't you want a protic solvents like acetone? Why? Why don't we want acetone, which is a protic? So why do we need solvents like water? For those who've forgotten what protic means, these are solvents which have hydrogens bonded onto electronegative elements like oxygen, nitrogen, or fluorine. So water, methanol, alcohols are protic solvents. Acetone, dimethyl sulfoxide, which is the relative to acetone, the difference is just the C and the S. These are aprotic. Acetonitrile, there's no hydrogen bonded directly onto nitrogen, oxygen, or fluorine. Those are aprotic. And we would want these aprotic solvents for SN2. These guys will be needed for SN2, while these ones will be needed for SN1. So let's see why. Okay, so polar, obviously water is polar, even these guys are polar, but polar protic solvents would be expected to help stabilize the transition state and the intermediates by lowering the activation energy. You know, in a reaction, like for the rate determining step, the higher you go, the harder the reaction will move forward. So you want to reduce this activation energy between the reactants and the first transition state. So considering protic solvent like water, take this to be a chlorine. Okay, so the protic solvent will tend the hydrogens of the protic solvents, like water, will tend to bind onto the halogen of the substrate. So really, what I should say is, I should show is, consider chlorine with its lone pairs on there. So that's a tertiary alkyl halide. If this substrate is in the environment of polar protic solvent like water, you definitely know, because of dipole moments, oxygen is partially negative, hydrogen is partially positive. Here, dipole moments pointed towards the chlorine. Chlorine will be partially negative, carbon will be partially positive. So you get some sort of attraction between the Cl and the hydrogen of the protic solvent, like in between here, you get an attraction. So eventually, you know, in SN1, this group has to fall off. So the hydrogen of the protic solvent is helping to pull out the chlorine, and that reduces the amount of energy to get to your transition state. Because instead of the Cl falling off by itself, actually the solvent is helping to pull out the Cl to make the carbocation. So protic solvents help to form the carbocation by pulling out the leaving group. So let me write that down. Protic solvents helps formation of the carbocation intermediate, and we want that for SN1. We don't want that for SN2. Protic solvents helps formation of carbocation intermediate by pulling out the leaving group. For example, pulling out Cl minus. And of course, that happens by H bonding. Okay? So you have some intermolecular force of attraction here. Could be H bonding or dipole, whichever intermolecular force happening there will help pull out that chloride. So that's one effect. So now assume this happens. Now you move forward, and now you have your carbocation. The Cl is gone, it's pulled out. So your carbocation will have a carbon center with a plus charge. The same protic solvent is useful here. Now we don't use the hydrogens anymore of the protic solvent. Now we use the oxygen. You know, the oxygen is partially negative. The carbocation is positive. So you get some sort of dipole, ion-dipole intermolecular force of attraction, which is what's happening on here. So donation of lone pair from solvent to the carbocation helps the carbocation to exist, because you're kind of quenching the plus character. The lone pair on the oxygen is bound or is donated to the C plus center. That stabilizes the carbocation. So key point. First, the protic solvent helps to pull out the leaving group. After the leaving group is gone, you form your carbocation. The protic solvent stabilizes the carbocation. And there's one other stabilization. Once the Cl goes out, the Cl is trapped by the hydrogens, again by hydrogen bonding. So those are kind of, I would say those are like 2 points or 3 points, so to speak. Pulling out the leaving group, stabilize the carbocation, and then stabilize the leaving group. After the leaving group is taken out, it's going to be like Cl minus. That Cl minus binds to the partially positive hydrogen of water, for example, by hydrogen bonding. So the solvent helps to keep the carbocation away from the leaving group. And now the nucleophile can come to attack. And guess who the nucleophile is? The water itself. This lone pair simply attacks the carbocation. And that's how you move forward to get an alcohol from the carbocation. Yes, ask.
The solvent pulls out the leaving group, and then it stabilizes the leaving group and also stabilizes the newly formed carbocation.
Yes, as it attacks it. As the solvent stabilizes the carbocation, it's going to use the lone pair on the oxygen to attack the carbocation. Let me take you back in the mechanism so you can see what I mean. You see here? You see how the water is attacking from the top of the back face? So it's stabilizing the carbocation, but at the same time it's attacking it. So you end up with this structure, and that structure moves forward to give you the alcohol. So that's what's happening in the flask. So you really need protic solvent for SN1 to happen. So that's what is described in all this mess here. The picture is describing that. So the solvent donates a lone pair to the carbocation, and by so doing, it's forming a bond. Of course, it's stabilizing the carbocation. That's what is happening here. At the same time, the solvent is pulling the chloride away from the alkyl halide starting material to form a carbocation. The same solvent will be used to stabilize the leaving group, to keep the leaving group away from attacking the carbocation, because this is Cl-. The Cl- might decide to come back and attack the C+. So the solvent is keeping it away so that the molecules of the same solvent will attack the carbocation. Too much science, but that's what's happening. Okay, so emphasizing on the solvent effect. So the higher the dielectric constant, which is a measure, it's a measure of the substance's ability to insulate the charges from each other. That's what the solvent is doing. It's taking the charges, the Cl-, the leaving group, away from the carbocation positive charge. It's insulating the charges from each other. The higher the dielectric constant, the higher the polarity. So obviously you see water has a dielectric constant of 78. Look at the rate, SN1 rate. Very fast, 8,000 value. Hexane, it's all carbon and hydrogens, 1, 2, 3, 4, 5, 6. It's completely nonpolar. The dielectric constant is 2.0. SN1 will tend to fail in a protic solvent like hexane. Acetone, dielectric constant is 21. The rate is just 1. That is not even comparable to the 8,000 or the 1,000 that you get with methanol. So that's why you don't want a protic solvents for SN1. Instead, one would want to use protic solvents. Of course, the more the carbons you add, the less the rate of reaction. Even though you have the OHs. The more the carbons you add on the solvent, the less the reaction, the SN1 rate of reaction will go. So just know the dielectric constant epsilon is the measure of that solvent molecule to insulate the charges from each other, which is the solvent effect that we just described here. Okay, so water is small and it has the two OHs on the structure. So you'll expect the two OHs to play a huge role in stabilizing or insulating the charges. That's why in water SN1 will really go super fast as compared to other solvents. Remember, aprotic solvents are disfavored, or the protic solvent disfavor SN1. Someone answered that question for me. Which of the following solvolysis reactions would you expect to have fastest rate of reaction? So let me help you out. Solvolysis reactions are reactions where the solvent takes part. Solvent takes part in reaction. That's what solvolysis reaction means. The solvent takes part in the reactions. So which of the following reactions where the solvent takes part in the reactions would you expect to have the fastest rate of reaction? What's the answer?
A.
It's gonna be A. Of course, we know all these guys are tertiaries, so don't even consider SN2. And it's gonna be A because A has, what happened? Okay, A has the most amount of protic solvent. That's what we want. You want one that has the most amount of protic solvent. So that's why the answer is 1. Look at the percentage, 80%, 50%, 20%. So A is the most reactive because it has the most amount of protic solvent. We are looking at SN1. It prefers protic solvents. Okay, I'll introduce this and stop it, and then I'll send you the post-class quizzes later on in the evening. So apart from what did we say? Apart from the leaving group, apart from the solvent, the other factor that affects rate of reaction is electronic factor. So here you want tertiary carbocation over secondary over primary over CH3. Of course, these carbocations come from alkyl halides. So right now, this one is a tertiary. All you have is 3 C's. So that's tertiary. This is secondary. That's primary. And then, of course, this is CH3 plus. These might have come from that when this falls off. This might have come from that. It could be BrCl, iodine, it doesn't matter. This might have come from that. Only one R group right there. And then this is just like CH3Br. So the more the alkyl substituents, the more stable the carbocation. The reason being, you are quenching the electron density. The R groups are donating electrons through bond by inductive effect. That neutralizes the plus charge. Because the electrons are negatively charged, they tend to reduce the plus character, positive character. So apart from the solvent using its lone pair to stabilize the C+, also the alkyl groups helps to do that. So we are considering electronic factors because it's the electron density that's going to be donated through the bond. So we term these electronic factors that affect SN1. So the greater the substitution, the more stabilization of the carbocation, and the lower the activation, the less the activation energy is going to be needed in the rate determining step. So you do want more substituents around the leaving group, on the carbon bearing the leaving group. That will stabilize the carbocation intermediate that is formed. Let's see. So I'm going to use this slide to end. So you see, the activation energy for a tertiary is less than the activation energy of a secondary, and that's going to be less than activation energy of a primary carbocation. And of course, methyl CH3 plus will have a higher transition activation energy. Now for sp2 and sp, they will be way high there. That's why I said you don't want to consider those. The activation energy will be so high for sp2. Sp carbocation will be even higher. So these ones, don't even consider them. So the higher the activation energy, the slower the reaction, because really the reaction has to overcome this mountain before it forms the carbocation intermediate. That's why the rate of reaction of SN1 will go with tertiary, low activation energy, than the methyl carbocation. The tertiary carbocation will have the least activation energy. So let me stop there. Oh, let's stop with this question. Someone give me the answer to this. Which of the following alkyl halides will be the most reactive in SN1? Answer?
4.
Yes, the reason being, once this falls off, you have 2 R groups, so this is secondary. But when the bromine falls off right here, you have 3 R groups. It doesn't matter how long the chain is. You have 3 carbons around the C+. This is tertiary. So the answer is 4. Obviously, this will give you a primary. This will give you a primary. So you don't want those. The answer is 4. Let's stop there for today.